Hey everyone, my name is Nathan, and on behalf of my collaborators, I'll be presenting our work on learning optimal and fair classification trees. So we're first motivated to further work of fair decision trees because there are many high impact domains that increasingly use machine learning in order to solve their classification tasks. So what I mean by high impact domains is typically situations where people's livelihoods are at stake. So a prime example here is in the United States, it's common to use an algorithm to predict a criminal's risk of recidivizing or repeating the same crime. And then that information then plays into a judge's decision on one's criminal sentence or probation. Another great example is the use of machine learning in the medical literature to diagnose and then treat illnesses. In both these cases, we believe that there are three facets that need to be satisfied. It needs to be accurate because we want to minimize the number of lives potentially altered for the worse. It needs to be interpretable because we want these decisions to be transparent and understandable. And it also has to be fair because in these problems, there are often groups of people who are historically marginalized, perhaps based on race or sex or other attribute. So the question we hope to solve with our approach is how to find the decision tree that maximizes accuracy while satisfying some notion of fairness that we impose in the learning problem. And I've been a bit hand-wavy about what constitutes as fair in this context, but I'll be a little more formal in the coming slides. So just to formulate the problem a little bit, it's actually quite similar to the regular machine learning context. So we have a feature vector X, classes Y, and in this case, we only consider the case of binary classes. But we additionally have a sensitive attribute P, which again could be race, sex, or any feature that must be protected from discrimination. So we learn from training data D, and hopefully our decisions will generalize to out of sample accuracy while also satisfying fairness with respect to sensitive attribute P. So, let's start talking about the definitions of fairness. The fairness literature actually has a lot of notions and definitions, but I'll cover three of them just to give an idea of how we can define fairness. The first and most common is statistical parity, which says that we should assign the same positive classification rate for each sensitive group. So for example, if a company wants to make its automated hiring algorithm more fair, they might require that males and females be hired at equal rates. Now, this is probably, again, the most common fairness notion, but it's quite simplistic. What if different groups behave differently? Or in other words, what if their distribution of risk is as different? One way to solve that is through conditional statistical parity, where we want the same positive classification rate for each group conditioned on factors indicative of risk. So if we use the same company hiring example again, let's say we have an additional attribute L that indicates some level of qualification the candidate has for the job. So among males and females who are unqualified, let's say we want the rate for hiring to be really low, but equal nonetheless. And it's the same logic for those with some qualification and those with very qualified. While the rate may be, and in fact should be different across these risk groups, they should be the same among the sensitive groups. But you can imagine still, even with conditional statistical parity, is that in the worst case, the rates in which we hire among the unqualified population is much higher than those who are qualified. So to solve this problem, we could incorporate another notion of fairness called equalized odds, which says that each group needs to have the same true positive rate and false positive rate. So basically, we're now taking into account the ground truth data so that our resulting decisions are fair, yet still somewhat faithful to the data. So our proposed approach is a mixed integer optimization formulation that follows this sort of flow graph design, where data points flow from source S through the tree and then down through the leaves here, where they're then assigned classes via their respective sync nodes T. So in this case, there are two classes, 1 and 2. You can see on the bottom right that we can add a constraint satisfying whatever fairness notion we please in the formulation. In this particular example, I incorporated the statistical parity constraint. And because of time, I'll skip the details of the actual MIO formulation. But in terms of our modeling advantages, I talked briefly about the first one, which is that it has it's very flexible to any fairness notion. And this capability we haven't really seen in the previous literature, which typically defines their method alongside 1 or 2 fairness metrics. We additionally allow for more than 2 sensitive groups to exist in our problem, whereas many prior methods only allow for 2 sensitive groups. And they sometimes incorporate a notion of dominant versus minority group as well, but our approach allows for more complex relationships between multiple groups. We also incorporate the fairness constraint within our learning problem, as opposed to pre or post-processing methods that don't really consider how the model itself becomes unfair. The works of Kanamori and Arimura, as well as Chang et al. Learn decision trees this way, or learn fair decision trees this way. And then finally, our method maximizes decision quality by solving to optimality, rather than heuristic-based methods that might be far from optimal. A notable work in this is Kamiran et al. So we benchmark our results to Kamiran et al.'s method because many other works in fair decision trees either did not have a code base at hand or just didn't really apply to our learning problem. And we ran a variety of experiments. So the figures you see here are just one of the experiments we did in the paper. So this slide here shows discrimination as a percentage on the x-axis, and then accuracy as well as a percentage as well on the y-axis. The solid red line shows the performance for our method, while the other lines correspond to different sub-approaches from Kamiran et al. And it's important to note that these are trees trained on maximum depth 2, meaning there are 2 levels of branching decisions. I'll synthesize the comparisons in a second, but I just wanted to show the results on trees with depth 3 as well, which are pretty similar. But to give a high-level interpretation of these figures, given a fixed discrimination threshold, our approach improves out-of-sample accuracy by around 2 percentage points on average, and always obtains higher out-of-sample accuracy in our experiments. Now, in high-stakes domains that we previously motivated our work on, a 2 percentage point improvement is quite important because it affects people's lives. Another interesting observation is that our approach in general created more heterogeneous results, meaning there are much more accuracy discrimination pair data points. This kind of allows practitioners to be able to finely tune between the accuracy and trade-off discrimination. Accuracy and discrimination trade-off. And for the interest of time, I'll just skip this. But thank you for listening.
I can hear you.
So if you fix the training set to get fairness in the training set, you get worse performances, but if you train an unfair training set, then you use your method.
Sorry, it's a little hard to hear from here.
So you pre-process your training set so that it is fair. Would that work? Would that work as well as what you propose?
Yeah. So as I mentioned, other methods, in the fairness machine learning literature, there's pre-processing steps that gets rid of fairness, that gets rid of bias in the data, and then there's post-processing steps, which gets rid of bias, which basically tweaks the model's prediction and then makes it more fair. So yes, there's a slew of other pre-processing methods that could work as well.
Which one?
And so the follow-up question is there one approach that is better than the other?
Well, I think that really depends, right? So for us, I think what we would argue is by incorporating the full data set, the full original data set into the learning problem, and then also imposing the fairness constraints within it, it would result in a more optimal and or results in decisions that are truer to the original data. Apart from the fact that, when you pre-process the data, you could basically run any machine learning model with it, which is okay. But in our context, since we really want optimality and interpretability, we decided to choose decision trees.
Anything else? Yes.
It kind of seems like you have to know what kind of bias you're looking for in the first place. What about some hidden biases that you cannot as easily identify by the group attributes you have? How do you try to detect those as well, or how do you deal with those?
I caught some of that. So you're saying that there are a variety of different biases that can occur in some data set. How can you sort of?
Because the ones you mentioned, they seemed like you already had a clue as to what kind of discrimination look to.
Can you automate the detection?
Yeah, that's true. That's true. So the data sets that we used were based off of previous works who had previously analyzed the type of bias that exists in that data. But typically what you can do is just split the segments of the populations in the data and then see what the historical classification has assigned them. So for example, if you have this recidivism data set and then Black defendants and white defendants are classified systematically discriminatorily in the data, then it seems then you can kind of infer that the data is biased towards white defendants. But there's a variety of ways you can.
If I can add a few words to answer your question. So in practice, how would you use this? You'd have like a specific application with specific practitioners you're working with. And based on your application, you'd say, well, this is the kind of fairness I need in my problem. We're not trying to say you want to eliminate all kinds of biases from your data set. This is actually not possible. So you want to say, for my application, this is the kind of like fairness I need. And then you train a tree that satisfies that fairness requirements. And then you tune like how fair you want to be relative how much accuracy you're willing to lose.
If everything is fair, you cannot know, right?
Basically, yeah, like so we know from like theory in machine learning that there's many fairness notions that you cannot have together anyway. So yeah, so this is not about saying, oh, we're going to eliminate all biases. This is you tailor your constraint to the specific application you care about.
Okay, we need to move on. Thank you. Thank you again.